For most of human history, the ocean has appeared as a smooth and shifting surface, vast, reflective, and seemingly empty. Yet beneath this moving layer lies one of the most complete records of Earth's history. Hidden in darkness, beyond light and immediate perception, the seafloor is slowly writing a timeline that extends back millions of years. Every grain of sediment, every layer of rock carries information about climates that no longer exist, oceans that have changed, and life that has evolved and disappeared. This record forms continuously, without interruption, shaped by processes so gradual they remain invisible within a human lifetime. And yet, when observed with care, these layers reveal patterns that connect distant events across geological time. In this documentary, we will follow that record downward, through formation, accumulation, and transformation, tracing how the seafloor becomes a quiet archive of the planet itself. If you find this kind of deep, slow exploration meaningful, consider subscribing to Physical Depth and supporting the video with a like or a share. It helps these calm scientific journeys reach more people. We begin where nothing seems to be recorded, at the surface of the ocean. From above, the ocean appears as a continuous and shifting surface, shaped by wind, light, and atmospheric motion. Its visible patterns change from moment to moment, giving little indication of what lies beneath. The surface reflects the sky, concealing the depth below in a uniform field of color and motion. Beneath this layer, however, the seafloor extends across vast distances, forming one of the most extensive environments on Earth. It is not a static boundary, but a structured landscape composed of ridges, plains, trenches, and slowly accumulating sediments. These features exist beyond direct observation, shaped over timescales that extend far beyond human experience. Unlike landscapes on land, where erosion and weathering continuously alter visible features, the deep ocean preserves materials in a more gradual and continuous manner. Fine particles settle through the water column, layer by layer, forming sequences that remain largely undisturbed. Over long periods, these layers begin to reflect changes in climate, biology, and geological activity. The ocean's surface does not reveal this process. It offers no immediate sign that a detailed record is forming below. Yet, across the seafloor, a quiet accumulation continues. Each layer contributes to a structure that, when observed carefully, provides a measured account of Earth's history, stored beneath a surface that appears, at first, unchanged. Far below the shifting surface of the ocean, the seafloor functions as a long-term repository of geological information. It does not record events in a deliberate or structured way, but through continuous natural processes that operate over extended periods of time. Each layer of sediment, each formation of rock, becomes part of an accumulating sequence that reflects changing conditions across the planet. This archive is formed through the gradual settling of particles from the water above. Dust carried by wind, minerals transported by rivers, and microscopic remains of marine organisms all descend slowly toward the ocean floor. Upon arrival, they form thin layers that, over time, build into a stratified record. The deeper the layer, the older its origin, creating a vertical timeline embedded within the sediment. In addition to physical material, the seafloor preserves chemical and biological signals. Variations in composition can indicate shifts in temperature, ocean chemistry, and biological productivity. These changes are not abrupt, but emerge as subtle differences between layers, requiring careful analysis to interpret. Unlike written records or surface features, this geological archive is not immediately visible. It must be accessed through indirect methods, such as core sampling and remote sensing. When examined in detail, however, the seafloor reveals a continuous and expansive record, one that documents Earth's history through accumulation rather than intention, preserved in the stillness of the deep ocean. The formation of layers on the seafloor occurs at a pace that is largely imperceptible within a human lifetime. Particles descend through the water column in a continuous but sparse movement, often measured in millimeters per 1,000 years. This slow accumulation creates a record that develops quietly, without visible change on short timescales. Each layer begins as a thin deposit of material settling onto the ocean floor. These materials vary in origin, including fine mineral dust, microscopic shells, and organic debris. Over time, they compress under their own weight, gradually forming more stable sedimentary structures. The process is steady and uninterrupted in many deep-sea environments, where external disturbances are limited. Because the rate of deposition is so low, individual layers may represent long intervals of time. A few centimeters of sediment can correspond to thousands or even millions of years. This compression of time into thin physical boundaries makes the seafloor a dense archive of historical information, though one that requires careful interpretation. The human sensory experience is not equipped to detect such gradual change. There are no immediate visual cues or rapid transformations to observe. Instead, the record forms continuously in the background, shaped by processes that operate far below the threshold of direct perception. In this way, the seafloor develops as a layered structure defined not by sudden events, but by persistent and nearly invisible accumulation across geological time. Beneath the ocean floor, time is expressed in a manner that differs from everyday human experience. The processes that shape the seafloor operate across intervals that extend far beyond years or centuries, unfolding instead over millions of years. These extended timescales are not immediately visible, but are embedded within the structure of sediments and the formation of oceanic crust. As layers accumulate, they create a vertical sequence in which depth corresponds to age. The uppermost sediments reflect relatively recent conditions, while deeper layers preserve increasingly distant periods in Earth's history. This arrangement allows the seafloor to function as a chronological system where time is organized spatially rather than observed directly. The oceanic crust itself follows a similar pattern. Formed at mid-ocean ridges and gradually moving outward, it records the passage of geological time through its position and composition. Younger crust is found near zones of formation, while older sections extend toward regions where the crust eventually returns to the interior of the Earth. These processes unfold at rates that remain constant over long durations. The movement of tectonic plates, the settling of particles, and the transformation of materials all contribute to a system in which time is measured through accumulation and displacement. Within this environment, time is not marked by distinct events, but by continuous progression. The seafloor preserves this progression in a form that can be studied, revealing a history defined by scale, duration, and steady change beneath the ocean surface. Across the global ocean floor, mid-ocean ridges form an extended network of elevated structures where new crust is continuously generated. These monads are not isolated features, but part of a connected system that spans thousands of kilometers beneath the ocean surface. Although hidden from direct view, they represent one of the primary sites of geological activity on Earth. At these ridges, tectonic plates gradually move apart. This separation allows material from the mantle to rise toward the surface, where it begins to cool upon contact with the surrounding seawater. The molten material solidifies into basalt, forming new sections of oceanic crust. This process does not occur abruptly, but is a steady and ongoing movement that continues over long periods of time. As new crust forms, it slowly moves away from the ridge axis. This outward motion creates space for additional material to emerge and solidify, maintaining a continuous cycle of formation. Over millions of years, this process contributes to the expansion of the ocean floor, establishing a pattern in which younger crust is located near the ridges, while older crust lies farther away. The structure of mid-ocean ridges reflects this dynamic environment. Their surfaces are shaped by repeated episodes of formation and coaling, resulting in a landscape defined by gradual elevation and subtle variation. Through this continuous creation, the seafloor does not remain fixed. Instead, it develops as an evolving system, where new material is steadily added, extending the geological record outward from its points of origin. As molten material rises beneath mid-ocean ridges, it encounters a rapid transition from the high temperatures of the mantle to the comparatively cold environment of the deep ocean. This shift initiates a series of cooling processes that lead to the formation of basalt, the dominant rock type of the oceanic crust. When magma reaches the seafloor, it is exposed directly to seawater, which absorbs heat efficiently. The outer surface of the heck-flowing material cools quickly, forming a solid boundary while the interior remains partially molten. This contrast between exterior and interior cooling produces characteristic structures known as pillow basalts, rounded, layered formations that accumulate as new material emerges and solidifies in sequence. Below the surface, cooling occurs more gradually. Magma that does not erupt fully may remain beneath the seafloor, where it cools at a slower rate. This allows minerals within the rock to organize into more defined crystalline structures, contributing to variations in texture between surface and subsurface layers. Over time, repeated cycles of eruption and cooling create a stratified crust composed of distinct but related formations. Each layer reflects the conditions under which it formed, including temperature, pressure, and the rate of heat loss to the surrounding environment. These processes do not produce abrupt or isolated features. Instead, they generate a continuous structure that develops incrementally, recording the conditions of its formation. Through basalt formation and cooling, the seafloor preserves not only its physical composition, but also a record of the thermal and geological processes that shape it. The formation of new oceanic crust at mid-ocean ridges is accompanied by a gradual outward movement, known as seafloor spreading. This process reflects the continuous motion of tectonic plates, which shift slowly across the surface of the Earth over extended periods of time. Although the movement is minimal on a human scale, it becomes significant when considered across millions of years. As basalt forms and solidifies along the ridge axis, it becomes part of a rigid plate structure. Over time, this newly formed crust is displaced laterally as additional material rises and cools behind it. The result is a steady expansion of the seafloor, with crust moving away from the ridge in both directions. This outward motion creates a symmetrical pattern, where younger rock remains close to the ridge and older rock is found at increasing distances. The rate of spreading varies between different regions, but it generally occurs at a pace of a few centimeters per year. This slow and consistent motion contributes to the large-scale rearrangement of ocean basins, influencing the distribution of continents and the shape of the seafloor. As plates continue to move, they interact with other boundaries, including zones where crust is compressed or drawn downward. These interactions form part of a broader tectonic system that governs the structure of the Earth's outer layer. Through seafloor spreading, the ocean floor is not static. It evolves continuously, carrying with it a spatial record of its formation and movement across geological time. While still above certain temperatures, these minerals remain unaligned. As cooling progresses, they gradually lock into orientation, preserving the direction of the magnetic field present at that moment. This process creates a stable magnetic signature within the newly formed rock. Over time, As more basalt emerges and solidifies, successive layers record successive magnetic conditions. Because the Earth's magnetic field has reversed polarity many times throughout its history, these changes become embedded within the seafloor as alternating patterns. When observed across large regions, the ocean floor reveals a series of parallel bands extending outward from mid-ocean ridges. These bands display symmetrical arrangements of magnetic orientation on either side of the ridge axis. The pattern reflects both the continuous formation of new crust and the periodic reversal of the magnetic field. The scale of these patterns is not immediately visible without specialized instruments. Through magnetic surveys, scientists are able to detect variations in the seafloor's magnetic properties, allowing the structure to be mapped with precision. These magnetic records do not form intentionally, yet they provide consistent and measurable evidence of geological processes. They confirm the outward movement of oceanic crust and establish a timeline that connects seafloor formation with changes in the Earth's magnetic field over extended periods of time. Above the seafloor, the ocean contains a continuous suspension of fine particles moving slowly through the water column. These materials originate from multiple sources, including mineral dust carried by wind, fragments transported by rivers, and microscopic remains of marine organisms. Though widely dispersed, they follow a gradual downward movement, driven by gravity. The descent of these particles is not rapid. Many remain suspended for extended periods, influenced by currents, turbulence, and variations in water density. Over time, however, a portion of this material settles toward the ocean floor. This process occurs continuously, forming a steady but nearly imperceptible flux from the surface to the depths. As particles approach the seafloor, their movement slows further in the stillness of the deep ocean. Upon contact, they accumulate as a thin layer, contributing to the gradual formation of sediment. Each addition is minimal in isolation, yet over long durations, these deposits build into structured sequences that reflect changing environmental conditions. The composition of descending material varies depending on location and time. In some regions, biological debris dominates, while in others, mineral particles are more prevalent. This variation influences the characteristics of the sediment that forms below. The descent of ocean sediments represents a continuous connection between the surface and the deep ocean. It transfers material, and with it, information, from active environments above to the stable conditions below. Through this slow and persistent movement, the foundation of the seafloor's layered record is established. Marine sediment on the seafloor reflects a combination of materials that originate from different environments, each contributing distinct characteristics to the overall structure. These sediments are commonly grouped based on their source, forming categories that help describe how material reaches and accumulates on the ocean floor. One major category consists of terregenous sediments derived from land. These materials include fine particles of rock and mineral fragments, transported by rivers, wind, and coastal erosion. My friends are dead, and me are dead, and food war. Once they enter the ocean, they may remain suspended for long periods before gradually settling, particularly in regions closer to continental margins. Another significant group is biogenic sediment, formed from the remains of marine organisms. Microscopic shells composed of calcium carbonate or silica sink after organisms complete their life cycles. Over time, these biological materials accumulate, creating layers that reflect patterns of productivity in the overlying waters. In addition to these, there are hydrogenous sediments, which form directly from chemical processes within seawater. Minerals precipitate out of solution under specific conditions, adding another component to the seafloor record. In certain areas, volcanic activity also contributes material, introducing ash and fragmented rock into the sediment layers. Each type of sediment carries information about its origin. When combined, they produce a composite record that reflects interactions between land, ocean, atmosphere, and biological systems. Through their varied sources, marine sediments provide a structured, yet complex account of the processes that shape the Earth's surface over time. A significant portion of seafloor sediment originates from biological activity in the upper layers of the ocean. Microscopic organisms, including phytoplankton and zooplankton, live within the sunlit zone, where they form the foundation of marine ecosystems. Over time, as these organisms complete their life cycles, their remains begin a gradual descent toward the ocean floor. Many of these organisms produce hard shells or skeletal structures composed of calcium carbonate or silica. When they sink, these materials contribute to the formation of biogenous sediments. The accumulation is slow but continuous, creating layers that reflect patterns of biological productivity in the surface waters above. The composition of these layers varies depending on environmental conditions. In regions where calcium carbonate-producing organisms dominate, sediments may be lighter in color and more uniform in structure. In other areas, where silica-based organisms are more prevalent, the resulting layers differ in texture and chemical composition. As biological material settles, it may undergo partial decomposition during its descent. Only a fraction reaches the seafloor intact, while the rest is recycled within the water column. This selective preservation influences the structure of the sedimentary record, leaving behind traces that represent both presence and absence. Over extended periods, these biological contributions form distinct sequences within the seafloor. They provide insight into past ocean conditions, including nutrient availability, temperature, and ecological balance. Through this process, life in the upper ocean becomes embedded within the deeper geological record, linking biological systems to long-term environmental change. The rate at which sediment accumulates on the seafloor is neither uniform nor constant. It varies across regions and through time, influenced by factors such as proximity to land, biological activity, ocean currents, and the depth of the water column. These variations determine how quickly layers form and how densely time is recorded within the sediment. In some areas, particularly near continental margins, accumulation rates are relatively higher. Rivers deliver continuous supplies of mineral particles, and coastal processes contribute additional material. In contrast, the deep ocean, far from land, often experiences much slower rates of deposition. Here, sediment may build at a pace measured in millimeters over thousands of years. Biological productivity also plays a significant role. Regions with abundant microscopic life can generate a steady supply of organic and skeletal material, increasing the rate of accumulation. Conversely, in less productive waters, sedimentation proceeds more slowly, resulting in thinner and more widely spaced layers. Over geological time, these differences influence how events are preserved. Periods of rapid accumulation may capture short-term changes with greater detail, while slower rates compress long intervals into thinner sequences. This uneven distribution of material requires careful interpretation when reconstructing past conditions. Despite these variations, the overall process remains continuous. Layer by layer, sediment builds across the seafloor, recording changes at rates that reflect the dynamic balance of environmental conditions. Through these accumulation patterns, time is not only preserved, but shaped into a structure that reveals both gradual trends and subtle shifts in Earth's history. Beyond their physical structure, Marine sediments contain chemical variations that reflect the conditions under which they formed. These variations are often subtle, expressed through differences in elemental composition and mineral content. When examined in sequence, they provide a record of changes in ocean chemistry over extended periods of time. As particles settle through the water column, they carry dissolved and particulate substances from the surrounding environment. Some elements become incorporated into mineral structures, while others attach to organic material. Once deposited, these components remain within the sediment, preserving a chemical snapshot of the ocean at the time of accumulation. The concentration of certain elements can indicate shifts in environmental conditions. For example, variations in trace metals may reflect changes in oxygen availability, while differences in carbonate content can suggest fluctuations in acidity or biological activity. These signals do not appear as distinct markers, but as gradual transitions between layers. Over time, additional processes may alter the original composition. Chemical reactions within the sediment, driven by pressure, temperature, and microbial activity, can redistribute elements or transform minerals. Despite these changes, many primary signals remain detectable, allowing patterns to be reconstructed with careful analysis. Through these chemical signatures, marine sediments extend beyond a physical record. They provide insight into the evolving state of the ocean, capturing changes that are not visible in structure alone, but are embedded within the composition of each layer. Within marine sediments, isotopes provide a refined method for interpreting past environmental conditions. Isotopes are forms of the same element that differ slightly in mass, and their relative proportions can shift in response to changes in temperature, biological activity, and ocean chemistry. These variations become incorporated into sediments as they form, preserving measurable signals over long periods of time. One of the most commonly studied systems involves oxygen isotopes found in the shells of microscopic marine organisms. As these organisms grow, they incorporate oxygen from seawater into their structures. The ratio between heavier and lighter isotopes reflects the temperature and composition of the surrounding water at the time of formation. When these organisms settle to the seafloor, their shells retain this isotopic signature within the sediment layers. Carbon isotopes provide additional insight. Variations in their ratios can indicate changes in biological productivity, as well as shifts in the global carbon cycle. These signals often correspond to broader environmental transitions, including fluctuations in climate and ocean circulation. Isotopic analysis requires precise measurement, as the differences between values are often small. However, when examined across multiple layers, consistent patterns begin to emerge. These patterns allow scientists to reconstruct sequences of environmental change with a level of detail not visible through physical observation alone. Through isotopes, marine sediments reveal not only what accumulated, but the conditions under which accumulation occurred, offering a calibrated record of past environments. Beneath the ocean floor, large quantities of carbon are stored within sediment layers and the upper sections of oceanic crust. This storage occurs through a combination of biological, chemical, and physical processes that operate over extended periods of time. Together, they form a long-term component of the global carbon cycle. A significant portion of this carbon originates from biological activity in the upper ocean. Microscopic organisms absorb carbon during their life processes, incorporating it into organic matter and skeletal structures. When these organisms settle to the seafloor, part of this material becomes buried within sediments, where it is gradually isolated from the active carbon exchange occurring at the surface. In addition to organic carbon, inorganic forms are also preserved. Calcium carbonate, produced by many marine organisms, accumulates as solid material within sediment layers. Over time, These deposits contribute to the formation of carbonate-rich sequences that store carbon in a stable mineral form. As sediment continues to build, deeper layers experience increasing pressure and temperature. These conditions can alter the structure of organic material, transforming it into more stable compounds. In some regions, carbon may also be stored within methane hydrates, where gas molecules are trapped within crystalline water structures under specific pressure and temperature conditions. The storage of carbon beneath the seafloor is not a static process, but part of a dynamic system. Some carbon remains buried for millions of years, while other portions may eventually return to the ocean or atmosphere through geological activity. In this way, the seafloor functions as both a reservoir and a regulator within the broader carbon cycle. Patterns of ocean circulation influence the distribution of heat, nutrients, and dissolved gases throughout the global ocean. Although these currents are not directly visible in the geological record, their presence can be inferred through subtle signals preserved within marine sediments. Over time, these signals form a layered record of how water masses have moved and interacted in the past. One source of information comes from variations in sediment composition. Different water masses carry distinct chemical characteristics, which can affect the materials that sand icy touch gives to this condition as a recipe. Changes in these characteristics over time may indicate shifts in circulation pathways, reflecting alterations in climate or large-scale ocean dynamics. Isotopic ratios also contribute to this reconstruction. As water moves through different regions, it acquires specific isotopic signatures based on temperature, salinity, and interaction with the atmosphere. These signatures can become incorporated into the shells of marine organisms, which later accumulate in sediment layers. When analyzed in sequence, they provide insight into changes in the origin and movement of ocean waters. In addition, the presence or absence of oxygen within sediments can reveal patterns of circulation. Well-oxygenated conditions suggest active water exchange, while low oxygen environments may indicate restricted flow or stagnation. These differences are preserved in the chemical structure of the sediment. Through the careful interpretation of these signals, the seafloor offers a record of ancient circulation systems. It reflects not only the movement of water, but the broader processes that shape the distribution of energy and matter within the ocean over geological time. At intervals within the continuous accumulation of marine sediment, distinct layers of volcanic ash appear. These deposits originate from eruptions that release fine particles high into the atmosphere, where they can be transported across large distances before settling onto the ocean surface. Over time, this material descends through the water column and becomes incorporated into the seafloor. Unlike the gradual deposition of typical sediments, volcanic ash is introduced over relatively short periods. This results in layers that are often more uniform and sharply defined than the surrounding material. Their composition differs as well, consisting primarily of fragmented volcanic glass and mineral particles formed during explosive eruptions. Because ash can be dispersed widely, a single eruptive event may leave a recognizable layer across multiple regions of the ocean. These layers serve as reference points within the sedimentary sequence, allowing correlations to be made between distant locations. When identified accurately, they provide a means of aligning timelines across separate records. The chemical composition of ash layers can also be analyzed to determine their source. Variations in mineral content and elemental ratios reflect the characteristics of the originating magma, offering insight into the nature of past volcanic activity. Once deposited, these layers remain relatively stable within the sediment structure. They mark moments of sudden input within an otherwise gradual system, preserving evidence of events that occurred on timescales much shorter than the surrounding record. Within the layered structure of marine sediments, certain intervals contain material that does not originate from the Earth's surface. These layers are associated with meteor impacts, events in which extraterrestrial objects enter the atmosphere and interact with the planet's surface. Although such events are infrequent, their effects can extend across large areas, including the ocean. When an impact occurs, it releases energy that can disperse fine particles into the atmosphere. Some of this material settles over the ocean, forming a thin but widespread layer within the sediment record. These deposits may include microscopic spherules, small, rounded particles formed from molten material that cooled rapidly during ejection and re-entry. In addition to physical structures, chemical indicators are often present. Certain elements, which are relatively rare in Earth's crust, but more common in extraterrestrial material, can appear in elevated concentrations within these layers. Their presence provides evidence of an external origin and helps distinguish impact-related deposits from other types of sediment. These layers are typically narrow in thickness, yet they represent events that occurred over very short durations. Their contrast with surrounding sediments allows them to function as temporal markers within the geological sequence. When identified across multiple locations, they can be used to correlate records and establish a shared reference point in time. Through these preserved traces, the seafloor records not only gradual processes, but also rare interactions between Earth and its surrounding environment in space. Within the continuous sequence of marine sediments, certain intervals reflect periods of widespread biological change. These intervals correspond to mass extinctions, when a significant proportion of Earth's species declined over relatively short geological timescales. Although the events themselves occurred in the biosphere, their effects are preserved in the structure and composition of the seafloor. One of the primary indicators is a shift in fossil content. Layers that once contained a diverse range of microscopic organisms may show a sudden reduction in variety and abundance. In some cases, entire groups disappear from the record, replaced in later layers by different assemblages. This transition marks a change in ecological conditions within the ocean. Chemical signals often accompany these biological changes. In the oceans, variations in carbon and other elemental ratios can indicate disruptions in the global carbon cycle, while changes in oxygen levels may suggest altered circulation or increased stagnation in certain regions. These factors contribute to environmental stress, which can be reflected in the sedimentary record. The boundary between layers associated with extinction events is sometimes marked by distinct material, such as ash or impact-related deposits. These markers help establish a temporal framework, linking biological changes to potential external or geological causes. Although mass extinctions represent periods of disruption, the sediment record remains continuous. It preserves both the decline and the gradual recovery that follows. Through these layers, the seafloor provides a measured account of how life has responded to large-scale environmental change over Earth's history. Not all sediment reaches the seafloor through slow and continuous descent. In certain environments, material is transported rapidly through underwater landslides and turbidity currents. These processes occur when accumulated sediment becomes unstable, often along continental slopes or submarine canyons, and begins to move downslope under the influence of gravity. An underwater landslide can be initiated by various factors, including seismic activity, oversteepening of sediment layers, or changes in pressure conditions. Once movement begins, large volumes of sediment may shift in a relatively short period of time. This displaced material can transition into a turbidity current, a dense flowing mixture of water and suspended particles that travels along the seafloor. As the current moves, it carries sediments across considerable distances before gradually losing energy. When the flow slows, particles settle out in sequence, with heavier materials depositing first, followed by finer grains. This process creates distinct layers known as graded bedding, where grain size decreases progressively from bottom to top. These deposits differ from typical deep-sea sediments, which accumulate slowly and uniformly. Instead, they represent episodic events that introduce thicker and more varied layers into the sediment record. Despite their abrupt formation, they become integrated into the overall structure of the seafloor. Through these processes, the seafloor records not only steady accumulation, but also intervals of rapid change, preserving the dynamics of sediment movement beneath the ocean. At the margins of tectonic plates, the seafloor descends into elongated depressions known as ocean trenches. These regions mark the locations where one plate moves beneath another, a process referred to as subduction. Although this movement occurs gradually, it represents a fundamental mechanism through which the oceanic crust is recycled into the interior of the Earth. Ocean trenches are among the deepest features on the planet, extending far below the surrounding seafloor. Their formation reflects the long-term convergence of plates, where older and denser oceanic crust bends and begins its descent. This downward motion is continuous, driven by differences in density and the broader dynamics of the Earth's lithosphere. As the descending plate moves into the mantle, it carries with it accumulated sediments and sections of oceanic crust. Some of this material is compressed and altered near the boundary, while other portions are transported deeper into the Earth. This process reduces the total extent of older seafloor, balancing the continuous creation of new crust at mid-ocean ridges. The environment within subduction zones is not uniform. Variations in temperature, pressure, and composition influence how materials are transformed during descent. These changes may include deformation, chemical alteration, and partial melting, each contributing to the ongoing evolution of the Earth's interior. Through subduction, the seafloor does not simply preserve history. It also participates in its transformation, gradually transferring surface records into deeper geological systems over extended periods of time. As oceanic crust moves away from mid-ocean ridges, it gradually approaches regions where it will be removed from the surface of the Earth. This process occurs at subduction zones, where the crust bends downward and begins its descent into the mantle. Over extended periods of time, this movement leads to the systematic destruction of older sections of the seafloor. The progression towards subduction is slow but continuous. Oceanic crust cools and becomes denser as it ages, increasing its tendency to sink beneath adjacent plates. When it reaches a trench, the leading edge begins to descend, carrying with it layers of sediment and altered basalt. This marks the transition from surface structure to internal recycling. During descent, the crust is subjected to increasing pressure and temperature. These conditions cause physical and chemical changes within the material. Minerals may reorganize, fluids can be released, and portions of the crust may partially melt. While some material is incorporated into the surrounding mantle, other components contribute to processes that influence volcanic activity above the subduction zone. Not all of the descending material is preserved in its original form. Much of the structure that once recorded surface conditions is gradually altered or lost. This transformation limits how far back in time the oceanic record can extend, as older crust is continuously removed. Through this process, the seafloor remains dynamic. Its history is not only written through accumulation, but also shaped by the steady removal and transformation of its oldest layers. The seafloor functions as a record of Earth's history, yet this record is neither complete nor uniformly preserved. Processes of accumulation and destruction operate simultaneously, shaping what remains accessible and what is gradually removed. As a result, The geological archive beneath the ocean reflects both continuity and limitation. In regions of stable deposition, sediment layers can remain relatively undisturbed for extended periods. These areas allow for the preservation of fine detail, where gradual changes in environment are recorded with clarity. However, such conditions are not universal. Disturbances such as underwater landslides, biological activity, or shifting currents can alter or erase portions of the record. More significant loss occurs at tectonic boundaries. As oceanic crust moves towards subduction zones, entire sections of the seafloor, along with their accumulated sediments, are drawn downward and transformed. In May 1754, we and France ester. This process removes older layers from the surface record, creating a natural limit to how far back the oceanic archive can extend. Despite these losses, preservation remains possible through selective conditions. Certain materials, such as microfossils or chemically stable compounds, can persist even when surrounding structures are altered. In some cases, fragments of oceanic crust may be uplifted onto continents, retaining portions of their original structure in a different setting. The geological record of the seafloor is therefore shaped by balance. It is defined not only by what is recorded, but also by what is removed. Through this interplay, the ocean preserves a history that is continuous in process, yet incomplete in detail, requiring careful interpretation to understand its full extent. Across the ocean floor, processes of formation and removal operate in parallel, maintaining a long-term balance within the Earth's outer layer. New oceanic crust is generated at mid-ocean ridges, while older crust is gradually drawn into subduction zones. This continuous cycle defines the structure and lifespan of the seafloor, shaping how geological records are created and preserved. The rate of crustal formation is closely matched by the rate of destruction. As new material emerges and spreads outward, it displaces older sections toward plate boundaries. Over time, this movement ensures that no portion of oceanic crust remains at the surface indefinitely. Instead, the seafloor is renewed through a process that replaces older layers with newly formed material. This balance has direct implications for the geological record. While sediments accumulate and preserve environmental information, the underlying crust on which they rest is transient. As it approaches subduction zones, both the crust and its overlying sediments may be altered or removed entirely. The record is therefore dynamic, shaped by both preservation and loss. Despite this impermanence, the process is continuous. At any given moment, new records are forming, even as older ones are being erased. The seafloor functions not as a permanent archive, but as an active system in which information is constantly generated, modified, and recycled. Through this balance, the Earth maintains a steady renewal of its surface. The history recorded beneath the ocean is not fixed, but part of an ongoing cycle that reflects the broader dynamics of the planet. Much of the seafloor's geological record lies beneath layers that cannot be observed directly. To access this record, scientists rely on deep-sea drilling and core sampling, methods that allow vertical sections of sediment and underlying rock to be extracted in a controlled manner. These samples provide a direct view into the structure and composition of the seafloor. Core sampling involves lowering specialized drilling equipment from research vessels to the ocean floor. Once in position, a cylindrical section of sediment is carefully cut and brought to the surface. Each core preserves a sequence of layers arranged from the youngest at the top to the oldest at the bottom, maintaining the chronological order formed during deposition. The analysis of these cores reveals multiple types of information. Physical characteristics such as grain size, color, and layering can indicate changes in sediment source and environmental conditions. Chemical and isotopic measurements provide further detail, allowing reconstruction of temperature, ocean chemistry, and biological activity over time. In deeper drilling operations, cores may extend beyond sediment into the oceanic crust. These samples offer insight into the processes of crust formation, alteration, and interaction with seawater. Together, sediment and rock cores form a continuous record that connects surface conditions with deeper geological structures. Although the extraction process is localized, the information obtained can be correlated across regions. By comparing cores from different locations, scientists are able to build a broader understanding of Earth's history as recorded beneath the ocean floor. The structure of the seafloor extends across vast areas that cannot be observed directly from the surface. To understand its form, scientists rely on mapping technologies that translate physical features into measurable data. These methods allow the seafloor to be visualized as a continuous landscape, revealing patterns that are otherwise hidden beneath the ocean. One of the primary techniques used is sonar mapping. By emitting sound waves from a vessel and measuring the time it takes for echoes to return, researchers can determine the depth and shape of the seafloor below. Repeated measurements across an area produce detailed maps that outline ridges, plains, trenches, and other large-scale structures. In addition to sonar, satellite-based observations contribute to this process. Variations in the Earth's gravitational field, influenced by the distribution of mass beneath the ocean, cause slight changes in sea surface height. These variations can be measured and used to infer the presence of underlying features, even in regions where direct mapping is limited. More localized studies may involve autonomous or remotely operated vehicles, which move close to the seafloor and collect high-resolution data. These systems can capture fine-scale details, including sediment patterns and small geological formations. Through the integration of these technologies, the seafloor becomes accessible in a systematic way. The resulting maps provide a framework for interpreting geological processes, allowing scientists to connect surface measurements with the deeper structures that record Earth's history beneath the ocean. The seafloor provides a structured record of Earth's history, but this record must be carefully interpreted to reconstruct a coherent timeline. Each layer of sediment and section of oceanic crust contains information tied to a specific period, yet these elements are distributed across vast and varied regions. To understand the sequence of events, scientists integrate data from multiple sources into a unified framework. Core samples play a central role in this process. By analyzing the physical, chemical, and biological characteristics of layered sediments, researchers can establish relative ages, identify which layers formed earlier and which formed later. These relative sequences are then refined through methods that assign approximate numerical ages, often based on isotopic measurements or known reference markers such as volcanic ash layers. Correlation between different locations is also essential. Similar patterns found in separate cores, such as distinctive chemical signals or fossil assemblages, allow layers to be aligned across large distances. This process extends the timeline beyond a single site, creating a broader and more continuous record of environmental change. In addition to sediment analysis, the movement of oceanic crust contributes to the reconstruction. The age and position of crustal sections provide context for how ocean basins have evolved over time, linking surface processes with deeper geological dynamics. Through the combination of these methods, a timeline emerges that is not directly observed, but inferred from consistent patterns. The seafloor, when studied in this way, becomes a coordinated record, allowing Earth's history to be traced across both space and time. In the present-day ocean, the process of sediment deposition continues without interruption. Particles from the atmosphere, land, and biological activity in surface waters are constantly entering the marine environment. Though individual contributions are small, their accumulation over time maintains the steady formation of new layers across the seafloor. This ongoing deposition reflects current environmental conditions. Dust carried by wind settles across open ocean regions, while rivers deliver mineral material to coastal areas. At the same time, microscopic marine organisms contribute organic and skeletal remains, linking biological processes at the surface with sediment formation at depth. Together, these inputs create a continuous transfer of material from active systems above to stable environments below. The rate and composition of deposition vary depending on location. In some regions, sediments accumulate more rapidly due to higher biological productivity or proximity to land. In others, particularly in the deep ocean, accumulation remains slow and evenly distributed. Despite these differences, the process itself remains consistent, forming new layers that will become part of the long-term geological record. Modern measurements allow this process to be observed with greater precision. Instruments placed in the water column can track the movement of particles, while seafloor sampling reveals the structure of recently formed sediments. Through continuous deposition, the seafloor is not only a record of the past, but also an active system in the present, steadily documenting ongoing changes within the Earth's environment. In recent centuries, human activity has begun to influence the composition and distribution of marine sediments. While natural processes of deposition continue, additional materials now enter the ocean through industrial, agricultural, and urban systems. These inputs, though recent in geological terms, are becoming integrated into the uppermost layers of the seafloor. Rivers carry increased quantities of sediment due to land use changes such as deforestation and construction. This material is transported to coastal environments, where it settles and contributes to altered patterns of accumulation. In some regions, the rate of deposition has increased, changing the structure of recent sediment layers. Chemical substances also enter the marine system. Trace metals, synthetic compounds, and other byproducts of human activity can attach to particles and become incorporated into sediments. These materials create detectable variations in composition, distinguishing modern layers from those formed under earlier conditions. In addition to chemical inputs, physical materials such as microplastics are now present in many parts of the ocean. These particles, derived from the breakdown of larger objects, settle alongside natural sediments. Their persistence introduces a new component to the geological record, one that reflects the presence of human activity on a global scale. Although these changes are recent, they are being recorded in the same manner as natural processes. The seafloor continues to accumulate material, now including signals associated with human influence. Over time, these layers will remain as part of the broader record, marking a distinct period within Earth's environmental history. The seafloor is often described as a record of the past, yet it also functions as an active system in the present. New material continues to arrive. Existing layers are gradually altered, and deeper structures are slowly transformed through geological processes. In this way, the seafloor is not a fixed archive, but one that evolves continuously over time. Each layer that forms becomes part of an ongoing sequence. Recent sediments reflect current environmental conditions, while deeper layers preserve earlier states of the ocean and atmosphere. Together, they create a vertical structure in which past and present are physically connected. This arrangement allows the seafloor to maintain a continuous record, even as it changes. At the same time, processes such as chemical alteration, biological activity, and tectonic movement continue to reshape the stored material. Some signals are preserved with clarity, while others are modified or reduced. The record is therefore dynamic, influenced by both accumulation and transformation. Despite these changes, the overall structure remains coherent. Patterns can still be identified, and long-term trends can be reconstructed through careful study. The seafloor retains its role as a source of information, even as it participates in the processes it records. As new layers form and older ones are gradually altered or removed, the seafloor continues to document the state of the Earth. It exists as a living geological archive, defined not by permanence, but by continuous formation, change, and preservation across time. As we return to the surface, the ocean once again appears calm and unchanged. Yet beneath it, the seafloor continues its quiet work, recording, preserving, and slowly reshaping the history of the planet. Each layer adds to a timeline that is never complete, but always extending. What has been lost is balanced by what continues to form. In this ongoing process, Earth does not simply hold its history. It continuously writes it, deep below the surface, in silence and over time.